This is Charge Tapes Revisited, Lab 2. My name is Amrita Kaur, and in this experiment, we revisit charge tapes and analyze how they can interact based on electric and gravitational forces. The goal of this experiment is to compare two charge distribution models with the point charge model and that treats the tape as a single point charge versus the line of charge model, which assumes that the charge is spread along the tape. In this experiment, the main concepts include Coulomb's law, which describes how electric force depends on charge and distance, Newton's second law, which uses gravitational electric forces to balance when the tape floats, and superposition principle, which states that the total force is the vector sum of all individual forces. A brief preview of the main result. For the computational model, we used the gravitational force set equal to the electric force, and from lab 1 we had that the overall charge was 2.05 times 10 to the negative 8 coulombs. This helped us compare of superposition versus point charges. So the assumptions and reasoning in this experiment was that air resistance is negligible. The tapes have equal charge magnitude. The charge is uniformly distributed along the tape, and that all other external forces are ignored. So for the experimental setup, our system consists of tape B, which is the floating tape, the system, and tape A, which is the stationary tape. The surroundings include the air, nearby objects, and external influences. For the procedure, the experiment followed these following steps. So the first one was to define the system parameters and constants, to generate the tape charges and assign their distribution, to compute the electric force on each segment, to identify equilibrium conditions, and then to finally run a GlowScript simulation to visualize the charge distribution. The one initial condition that was set for this is that the net force on the system is 0. These were the main data and calculations that we went in with. There was the key measured and calculated values, which included the tape length, as seen below, the tape width, the surface area, and the tape weight, as seen on the slide. Using those, we were able to calculate the charge Q, which was equal to 1.917 times 10 to the negative 8th coulombs, as well as the charge per atom, which was calculated as 1.198 times 10 to the 11th coulombs over 2.7 times 10 to the 17th atoms to get a ratio. So for the computational model, this was the code that we used, and that was used to determine the charge distribution and forces. The charge on one tape segment was calculated as 1.86 times 10 to the negative 8th coulombs using GlowScript. This is another showing all the code that we used. So for the results and conclusions, the results indicate that the charge distribution was not perfectly equal between the tapes, and that the point charge approximation was also not entirely accurate. So therefore, the charge model that was used in this lab was just much more precise than lab 1, even though it still had some discrepancies similar to the ones from lab 1. The possible sources of error were also that the charge distribution was just unequal along the entirety of the tape, or some computational and algorithmic errors within the modeling. So if we had modeled the tape as a point charge, the total difference would have been 0.04945 coulombs compared to our findings. This is the additional question that what if the tapes were modeled as a point charge? For the second additional question as to why do these numbers differ in the lab, this is because the charges were not modeled as a singular point charge. They were modeled as evenly distributed throughout the entire tape. So this would be more similar to what we would find in real life, since the impact of the electric field is much larger, and this is also why the findings from this lab are more accurate than what we had found from last week. So that is it for this lab. This was a more accurate way to model charge distribution among computational tools, and this results align more closely with real-world physics than the previous model that we had used. Thank you.